Okay, let's look at section 2 here, graphs of polar equations. I'm going to go really fast because you can pause and rewind and rewatch any part of this video here. Let's get going. Hopefully you have your calculator with you. I'll walk you through how to get that all set up here. Sketch a graph of the equation x is equal to 3 and express the equation in rectangular coordinates. All right, so don't worry about that second part. We'll take care of that eventually. Just like you started with equations in rectangular form, here's an equation. Don't know what it looks like. Make a chart of values. In this case, all you really need to do is be literate as far as math is concerned and just keep reading that equation over and over and over again. So if theta is equal to 0, r equals 3. If theta is equal to pi over 4, r equals 3. If theta is equal to pi over 2, r equals 3. If theta is equal to pi, r is equal to 3. If theta is equal to 3 pi over 2, r is equal to 3. If theta is equal to 2 pi, r is equal to 3. I'm just reading that equation over and over again, and now I have 6 different points to plot. So for 3, 0, again, 0 here is our starting polar axis, and I'm supposed to come forward 1, 2, 3 spaces, put a point. This is rotating around a pi over 4. Again, my radius is 3, 1, 2, 3, put a point. For pi over 2, up here, come forward on this ray in this direction, 1, 2, 3 spaces. For pi, it's over here, forward along the pi line, pi over 3. Hopefully you get a sense here that, all right, that's a grand total of 6 points plotted. Well, I kind of cheated with that last one. 3, 0, and 3, 2 pi. Those are the same point. This is a circle. If I put in more and more and more points, it's just going to fill that in. Okay, the radius is equal to 3. It's a circle centered at the pole. So, second part, not any more circles. We're given the polar version, r equals 3. Of the substitution formulas that we've talked about before, we don't have anything for just plain r, but we do have something for r squared. So what happens if we multiply, well, I'm sorry, we square both sides. It's not multiplied by anything. So r squared is equal to 9. Then we can do our lovely substitution. R squared is equal to x squared plus y squared. That's our equation. Hopefully you remember from your study of conic sections. Back in Algebra 2, that's standard form for the equation of a circle, where it is centered at the point HK. And again, the radius is the square root of that constant there. Well, again, if h is 0, we don't write x minus 0 squared. We just write x squared. If k is 0, we don't write y minus 0, the quantity squared. We just write y squared. So this is the equation for a circle. Now, again, convert what you see here in polar form back to rectangular form. It's a circle centered at 0, 0 with a radius of, you guessed it, 3. So in general, the graphs of equations of the form r is equal to 2a sine theta, or r is equal to 2a cosine theta, are all going to be circles. Now, there's some interesting things with those circles. I'm going to put in a new page of graphs. But immediately I see an issue here because it says f of x. I don't want to draw a graph here of something that's a function in terms of x and y, f of x. I need a polar graph. So if I come over to my menu function, I'm looking at, oh, again, hopefully you remember some of this analyze stuff where we can find points of intersections, max and min and zeros. Trace is always fun. Option 4 there, where we change the window settings to try and get things to fit. What we need right now is option number 3. We're not graphing a function or a relation. We are going, look at that, option number 5, our polar graphs. And you see here how things have immediately changed. Now that second line, we'll get to that in the next lesson. But in this case, notice here how this is not f of x. This is some kind of a function here, r of theta. Now if I go back to my notes here, say I want to graph r is equal to 6 cosine theta. So obviously the 6 from our trig, cosine. But now I can't type in x. This has to be a function of theta. Where is theta, you're wondering? Theta being a Greek letter, if I go back to the pi button that we use so much in the first semester, did you even notice of the hundreds of times that this has other options here? There's the theta. So I need to come over there and grab that, put that in there, and lo and behold, as advertised, this is a circle. Now, how about some points on that circle? Okay, what our notes are telling us here, since I typed in and I graphed the cosine, it's going to have a radius of the absolute value of a. So in this case, well, again, this says 6 cosine theta, so that would be 2 times 3 cosine theta, which means my radius is 3. And notice, again, with our lovely graphing calculator, it's not centered at the origin. It's not centered at 0, 0. It's not centered at the pole, if we're thinking of this in polar form. This has to be centered. Now, again, if it's the sine function, it's going to be centered at a comma pi over 2. If it's the cosine function, it's going to be at a 0. So the center here is at 3, 0. And again, don't get confused. That's not a y coordinate. That's an angle. That's a theta. So for 0 theta, that's right here on our polar axis. And we come forward 3 spaces. There's the center, and the radius is 3. All right, let's sketch a graph of r is equal to 2 plus 2 cosine theta. Now you'll have to remember a little bit of your trigonometry, or if you don't want to think that much, plug it in. The cosine of 0 radians is 1. So then we do the lovely algebra here. So this is 2 plus 2 times 1. Well, 2 times 2 will give us 2. 2 plus 2 is 4. So I need to plot the point 4, 0. And then if I say pi over 2, the cosine of pi over 2 is 0. Well, 2 times 0 is 0. 2 plus 0 is 2. I then go, say, to pi. The cosine of pi is -1. 2 times -1 is -2. 2 plus -2, that gives me 0. Now, if I take a moment here and plot those points, so again, for 0 theta, our polar axis here, I need to come forward 1, 2, 3, 4 spaces. So that's the point 4, 0. For 2 pi over 2, rotate around, here's pi over 2 again. I need to come forward 2 spaces. And for the next point here, I rotate around to the pi direction here, but my radius is 0. That means I don't move off the pole. Well, those 3 points really don't give me a good idea of what's going on here. So if I want to go back and find out more about this curve, I need to fill in more details. For pi over 4, if I take the cosine of pi over 4, that is square root of 2 over 2. Square root of 2 over 2 times 2 will give me square root of 2. 2 plus square root of 2. All right, I'm going to attempt to graph this. I can't leave that in simplest radical form. I need a decimal approximation. So type that in your calculator there. I believe square root of 2 will give us about 1.4142, blah, blah, blah. Add 2 to that, so we'll get 3.4. Okay. So if I plot that, again, find the correct angle here, the correct direction, and then I need to come out 1, 2, 3.4 spaces. What happens here? 1 pi over 4, 2 pi over 4. What about 3 pi over 4? 3 pi over 4 is in quadrant number 2. The cosine function in the second quadrant should be negative. So all I got to do is change the sign on that sucker, which means changing the sign on that. 2 minus square root of 2 should give me approximately 0.6. Again, use your calculator. Now this one is getting harder and harder to graph because here's the direction for 3 pi over 4, but I'm supposed to come forward only 6/10 of a space. Okay? So I had a radius here of 4. It shrunk down to 3.4, then to 2, then to 0.6, then to nothing. Well, if I continue this pattern here, how about 5 pi over 4? That's quadrant 3. Cosine in the third quadrant is negative. You know, come to think of it, it's the exact same value that we just got here. That's 0.6. For 3 pi over 2, the cosine of 3 pi over 2 is back up to 0. So 2 times 0 is 0. 2 plus 0 is 2. If I do 7 pi over 4, that puts me in the middle of quadrant number 4. Cosine in the fourth quadrant, though, turns back to positive. So, okay, so this is positive. That's addition. 2 plus, we did that already. 3.4. And of course, 2 pi, it's the same thing as 0. We'll be back to 4. So if I try and plot those, this is only 0.6-ish. For 3 pi over 2, I'm supposed to come forward 2 spaces. For 7 pi over 4, come forward 1, 2, 3.4 spaces, and then back to here. If we play connect the dots, we'll get this shape. You've never seen that before in your entire lives. Because, again, going back to keep referring to this, if we took r is equal to 2 plus 2 cosine theta, and tried to convert that into rectangular form, it would be hideously messy. Here in polar form, it's pretty short, and it gives us this very, very interesting graph here. Two plus 2, I forget which function I was using, cosine theta. Again, as you're watching this, pay attention to that red button over there. That tells you the last one I pushed. This graph is called a cardioid. Now, if you tilt your head severely to the left, it might remind you of a heart shape. Well, yeah, the heart shape, not the actual shape of an anatomically correct heart. That's what we call it. That's what you've got to remember. So this is a cardioid. Yay, 3 vowels in a row, because, that's what we do in math. In general, the graph of any equation of this form, r is equal to a times the quantity. Again, they've got it written in factored form here, so maybe it'll make more sense if it's a plus or minus a cosine theta, or if we have a plus or minus a sine theta. So those two values there, just like we saw a moment ago, the 2 and the 2, those are the same. It's going to turn out to be an interesting cardioid. Okay, now let's compare this with, I want to draw the graph here quickly, of 3 minus 3 sine theta. So if can I do this in the same one? 3 minus 3 sine of theta. Now, okay, maybe that one looks a little bit closer to a heart shape, and I don't think the pink is what does it. Okay, so you notice here how the cosine one looked like it was symmetric here up and down, but the pink one here for the sine graph looks symmetric left and right. Okay, that idea of symmetry is something that we'll come back to in the second half of this section. Okay, what about, instead of messing around with the coefficient in front of the cosine, let's start messing around with the coefficient in front of theta itself. Put in 0 in place of theta. Well, 2 times 0 is still 0. Cosine of 0 is 1. We put in pi over 2. Now again, algebra here, 2 times pi over 2 is pi. The cosine of pi is -1. Substitute pi in place of theta. Well, gee, 2 times pi is, well, 2 pi. The cosine of 2 pi is 1. Oh, that's not helpful at all. Okay. Now I'm going to use, because these numbers are really small for the radii, I'm going to go maybe to a bigger scale here so that the red circles are one space. So I have the point 1, 0, so that's here. For pi over 2, again, this is pi over 2. But now my radius is 1, so I have to go back one space. For pi, I come forward one space. And oh my goodness, that doesn't tell me anything. So I need more information. I need more data here. So if I say put in pi over 4, well, 2 times pi over 4 is pi over 2. the cosine of pi over 2 is 0. All right, well, again, that's interesting in that I was out here at 1, 0, and as I rotate around to pi over 4, that goes down to nothing. Okay, 3 pi over 4 multiplied by 2 will give me 3 pi over 2. The cosine of 3 pi over 2 is again 0. So for 3 pi over 4, okay. What happened in between here? What happened in between here? What happens in between here? Okay, need a lot more information on this one here. Turns out we start messing around with that coefficient on theta. Now I'm going to zoom in a little bit because, again, it seemed like making that table of values, our maximum value there was only 1. We've got ourselves some sort of little flower here. Okay. So again, it contains those points that I graphed before with 1, 0. And for pi over 4, it was back to 0. And then for pi over 2, it's down here at -1. So here's a chance where I think the trace function actually helps us. Now again, if you can see down here in the bottom corner, it's giving me coordinates. Sometimes they're approximated, but all right, so we have the point 1, 0. Again, we had that on our chart. But if I trace the graph here, notice what happens. As I get closer and closer to pi over 4, okay, well, it missed it by just a little bit here. So we were out here at the end of this. The term that mathematicians came up with here is this is a leaf. Okay, so this was the farthest point out, and I put in different angle measures here, substitute that into the equation. The radius gets smaller and smaller, and again, we saw for pi over 4, it's back to 0. Now notice here where it goes from there. We go to the pi over 2, -1. And then for 3 pi over 4, the radius was back to 0, but it continues. Okay, so again, here's our 1 pi. And for 3 pi over 2, it's -1. And finishing it up so that it just repeats over and over and over and over again. Because again, we're using the cyclical cosine function. Okay? I think it's beneficial for you to see the order in which those things get graphed. So what we have here is, yeah, I don't care if you agree with it or not. This is the term. We all have to use it. That shape is called a rose. Okay. So again, we can, I'm going to use the calculator here in a moment to show you how we mess around with that stuff. So if it's, again, A, could be anything there, nice constant, cosine n theta, or A is equal to n, a sine n theta, it's going to be a rose. Now, interesting things happen here, whether n is even or odd. All right, so here's cosine 2 times theta, and it actually turns out to have 4 leaves. If I then want to look at, I'm sorry, we're just going to do cosine 4 theta. We now have 1, 2, 3, 4, 5, 6, 7, 8 leaves on that rows. Okay, so for 2 times theta, we get 4 leaves. For 4 times theta, we get 8 leaves. What if I, instead of 4, I change that down to 3? We only get 3. What's up with that? So this is what, again, the printed part here is telling us. If n is an odd number, the number of leaves that we get for our rows is equal to that odd number. Okay, so you just saw there cosine 3n, that gives you 3 leaves. But if n is an even number, you double it, that's how many leaves we get. Okay, so again, for 2 theta, we get 4 leaves. For 3 theta, we only get 3. Now, if I boom, boom, go back, so that's the same. So 2 theta, that should give us 4 leaves. But if I change this, oh yeah, let's just go 3 times the cosine of 2 theta. So again, this is telling us here there's a possibility of having a coefficient here in front of either the sine or the cosine function. What's that do for us? It increases the size. Now I need to change my scale here so that you can see this. The same exact type of symmetry. We have this leaf centered on the polar axis. This one centered on theta is pi over 2. This one at pi. This one centered at 3 pi over 2. But now, with the orange one, by changing that coefficient on the cosine function, I've just increased the size of the leaves. Instead of the 0.10, we have the 0.30 here. Instead of pi, sorry, 1 pi, now I have 3 pi. Okay, so that's what the effect is there for that. All right, and again, it could be sine or it could be cosine to get us these roses. Let's compare what happens with those functions. So again, if this was cosine, I'm going to change this second one here to the sine function. Oh, yeah, it doesn't like it when I do that. Let's do sine 2 theta and compare that with the cosine of 2 theta. That's the green one. Oh, now I'm going to have to zoom in a little bit here. So you notice the differences here. For the cosine function appears to be centered there on, again, the polar axis, pi over 2, and 3 pi over 2. For the sine function here, for the roses, the leaves are centered on the pi over 4 multiples. Okay, so it's in between the leaves for the cosine function. All right, so I'm hoping all that makes sense. I'm hoping we get a good sense here. Part of your challenge. Yeah, you can plug that into the calculator. The calculator will draw you a lovely picture. How do you get that picture then onto, say, a piece of paper for a quiz or on your surface there? What I'm looking for is exactly what I've been drawing for you here. Make a table of values. In this case, I'm not even going to say label or table because to label the points on there is really going to obscure the graph. Um, some of these equations are going to be so simple, they will be lines. Some of them are going to be pretty easy circles. Some of these are going to be shapes that you've never seen before. Again, that's the whole point of learning this. We're doing new stuff you haven't done before. So if you scroll down to near the very bottom of your OneNote that I sent you, okay, it gives you these wonderful summaries, and my goodness, there's a lot of information packed into this. So if it's just r is equal to a, yeah, that's a circle. We did that with r equals 3. And then we looked at a cosine function here where the center isn't at the pole, it's been moved over here. And for sine, it's going to look like this, where it's moved up somewhere here on the theta is equal to pi over 2 line. Or, yeah, that'll be fun when you get to that one, graph a spiral. So here we have the cardioids. Um, again, messing around there. If A and B aren't the same exact value, then we get this little thing. And again, we'll talk about this next class, and I'll teach you a little bit of French. Here's some examples of roses. Okay, so a three-leaved rose here, four-leaved rose because that's two, three because that's three. Here we have an eight-leaved rose because it's four, and here we have a five-leaved rose because it's five. Okay, so there's all kinds of different things, really unique curves, interesting shapes. We're going to talk about symmetry because, oh my goodness, there's so much to discuss there. So, again, for next class, I'm splitting up all of these possibilities. This is a very dense section here. I'm splitting this up into two assignments. Okay, so try those 12 different graphs there. Again, this starts on page 553. If you don't want you to use your textbook at home, then again, go to portals down at the very bottom under documents. I've posted the digital version of the chapter 8 textbook. Good luck with that. We'll talk about it next time.